Now we're going to establish a relationship between the brightness of a point in the scene and its brightness in the image. The brightness in the scene is called scene radiance. The brightness in the image is proportional to what's called image irradiance, which is the flux falling per unit area in the image. So let's look at the problem itself. We have a surface right here, and in particular this point, which has an orientation n. The point is illuminated by this light source from this direction, and that produces a radiance in the direction of the camera. The radiance of the point is L. And this scene radiance is being projected by the lens of the camera to the image plane to produce an image irradiance or image brightness, E. So we want to understand the relationship between L and E. So let's set up this problem here. Here is our lens camera. We have a surface in the scene that we are observing. We have the lens and we have the image plane. We'll assume that the distance between the lens and the image plane is f. That's the effective focal length. Remember, that's not the focal length of the lens. It's the effective focal length of the imaging system. And let's assume that we are looking at the intensity captured by this pixel right here. And the pixel has an area DAI. And this pixel is observing, and this is through perspective projection, is observing this patch in the scene which has an area DAS. And let's assume that this patch has an orientation N, and that makes an angle theta with respect to the line of sight, which is the yellow line shown right here. And the line of sight itself makes an angle alpha with respect to the optical axis. And the depth of this patch with respect to the lens is Z right here. So what we're going to do is derive a set of equations, and that will lead to the relationship between scene radiance and image irradiance. So the first one relates to the solid angle subtended by the patch with respect to the lens. That solid angle is d omega s. And the solid angle subtended by the pixel with respect to the lens is d omega I. We can see from this diagram that d omega I is equal to d omega s. And we can also write the expression for each one of these. D omega I is dAI cosine alpha, that's the foreshortened area, divided by this distance squared. And what is this distance? It is f divided by cosine alpha. So f divided by cosine alpha squared. And that's equal to dAs cosine theta, which is the foreshortened area of this patch, as seen from the center here, divided by this distance squared. And that distance is z divided by cosine alpha. So dc divided by cosine alpha squared. And that gives us a simple expression. We'll call that equation 1. And now we're going to look at the solid angle subtended by the lens from the surface point, the patch right here. So let's say that the lens has a diameter d, and we are interested in this solid angle subtended by the lens as seen from the scene point of interest. So this solid angle is the area of the lens, which is pi d squared divided by 4, pi d squared divided by 4, cosine alpha, that's the foreshortened area of the lens, divided by this distance squared, which is z divided by cosine alpha squared. So that's equation 2. And now we know that the flux, the light flux received by the lens from this patch, DAS, is all going to be projected to the pixel DAI. So the light flux received by the lens from DAS is equal to the light flux projected onto the pixel with area DAI. Okay, so how do we figure out what is the flux received by the lens? Well, let's say that we know that the radiance of this patch is L. We know the definition of radiance, d2 phi divided by dAs cosine theta, dAs cosine theta, d omega L, which is the solid angle subtended by the lens. And so that gives us an expression for the flux received by the lens. That's equation 3. And this flux received by the lens is going to go, it gets bent by the lens and it falls on the pixel with area dAI, and therefore the image irradiance, which is the irradiance at this pixel, is the flux received by the pixel divided by the area of the pixel dAI. So that is equation 4. So you have these 4 very simple expressions, and from these 4 expressions, we can derive the relationship between scene radiance L and image irradiance E. Turns out to be this expression right here. So let's take a closer look at this expression. Here you have image irradiance, you have scene radiance, and this, remember, is the diameter of the lens, and this is the effective focal length. When you have the focal length of a lens divided by the diameter of the lens, we know that's called the F number. Here you have the focal length divided by, the effective focal length divided by the diameter of the lens. That would be the effective F number, and it's 1 over that, so we'll call it 1 over the effective F number right here. Okay, so a couple of things to observe here. One is that, fortunately for us, image irradiance is proportional to scene radiance, and that we sort of may have guessed, and it happens to be true. The second is that image irradiance falls off from the center of the image. That is, as you move away from the center of the image, the optical axis, this angle alpha increases, and you have this term here, which is cosine to the power of 4 alpha. So it begins to fall off. Now, of course, this is in the case of a single lens, and when you design a compound lens, you compensate for this effect. And the fall off is small as long as the field of view is small. So that brings us to an interesting question, which is, does image brightness vary with scene depth? In other words, as you pull a camera away from a scene, does the brightness of a scene point change? Intuitively, we might think that it should, because after all, you're moving away and therefore perhaps collecting less light. But if you look at this expression right here, you see that the distance between the lens and the point in the scene, which we call Z in our diagram, doesn't actually show up in this expression at all. And therefore, image brightness does not seem to vary with scene depth. That's interesting. So let's take a look at why that's the case. So let's say that this is our setup right here. You have a scene and you have your camera, and let's say your camera has a single pixel. So we've exaggerated that pixel, made it really big, and let's assume that the area on the scene that is projected onto this pixel is this area right here. Now, if you pull this camera back, that area is of course going to increase. So in other words, that same pixel is going to be accumulating light from a larger area in the scene, which almost seems to imply that the brightness of the pixel is going to increase, and that we know is not the case. So what's going on here? So this says that the larger the scene depth, the larger the area of light accumulation. But on the other hand, we also have the solid angle subtended by the lens from each point in the scene. And so that's this solid angle right here. And that also governs how much light is being collected by each point in the scene. That's pretty large here, but as you move back, that solid angle decreases. So while you're actually collecting light from a larger area, that is, a pixel accumulates light from a larger area as you move back, from each point within that area, it's actually collecting less light because the solid angle that the lens subtends with respect to each point is actually dropping. These two effects cancel each other, as a result of which image irradiance is independent of scene depth. Very interesting property.